what I do at Ubisoft is I work on speech synthesis, and this is how we approach the problem of controlling the style of the synthesis in speech. Um, so there will be three parts to the speech. First, I'm just gonna do some preliminary explanation on why we do this and how it all fits in the game, video games. And then we're gonna dive into controlling the style and just some closing remark on what is ahead for research. So just a quick bit about me. I'm a research scientist at Laforge, which is one of the research lab in Ubisoft. There is one in Toronto, in the studio of Toronto. There is a Laforge lab, and there are a new one in Bordeaux also in France. So what we do is we collaborate with the academia. We take everything that we can find in latest research of academia and of interns and collaboration with professor and all of this, and we see how it can fit to create a prototype that can prove to be useful for video games. And on the other side, we have also people from the company who mix in and industrialize the research. So the idea is to put people from both worlds in the same place. And I, as a research scientist, I make sure that something nice, hopefully something nice, comes out of this. So my background is I did electronic engineering. I was a hardware engineer for a decade, and then I did a PhD on. It's called multiple instance learning. It's some kind of weakly supervised learning. It's a type of machine learning. I don't really use it at work, so I just wanted to say that usually I do a deep dive machine learning. So what's speech synthesis? I guess you all know, but it's always nice to define stuff. So it's just it encompasses everything that is producing human speech by artificial means. The most common application that you see is text to speech. Just input text and have a machine say it, and voice conversion, which sometimes is referred to as speech to speech. In that case, you're just repeating what you have been hearing, but with the voice of another person. And this little diagram is another type that we don't see anymore. In that case, it's the Volder. It's in the 50s, I think, if I remember correctly. And it's a speech synthesis, but that time it's an operator that is it's driving a mechanical machine. If you type Volder in YouTube, you can go see. It's interesting. So why are we interested at speech synthesis in video games? There are many uses. First, we use it as placeholder when we develop a game. It can take up to 3 years, sometimes more. And we are like fiddling with the scenario, the narrative content. So you cannot start recording final lines right away, but you still need to work on the game. So having some sorts of a replacement, like a temporary replacement for the real line, it helps you debug, because you have real wave file that you can work on. And also when you are trying to see if your story fits together and how it plays out in the game, it's fun to be able to listen to the lines, even if they are not as good as made by a real actor. So you can use it to iterate on the content. And of course, if you do like alphas or first play, like demos that we do internally to make sure that the game is up to standard, and it's fun to have voice also. So this is one reason. The other reason is we have to provide support for accessibility. So some people have difficulty reading menus and chat and stuff like this. So this is mandatory as of now to provide this kind of service. One of the reasons maybe for the future is that we are always building bigger and bigger world. most modern AAA games, AAA game means like a high budget game. They have more than 100,000 lines per game. Sometimes it goes up to 200, 250, and we have to do it in our case often 7 language. So in the end, you realize that it's a very very big amount of work that we need to do: the casting, the recording, the cleaning, and all of this. And at some point, it's not. It's just that it won't be possible to make a world bigger in 3 years, just because it's impossible in man hours. So we have to find a way to make it possible, and maybe speech synthesis can be a way. And those were more technical reason, and of course there's the fun stuff. It's the fact that if you can synthesize your characters, then it's possible to iterate very faster in the game, much faster in the game, so you can add content on live events every week. There could be new stuff happening in your world. You can also have special lines that are personalized to the player depending on your own story. So you don't have to listen to a pre-recorded scenario. There are people who would like to be able to change their voice in game, have a voice skins, and you can choose how your character talks. And also new interaction mode, so you can think about. I often refer to Google Duplex. If you ever watch this demo, it's a person. In fact it's a robot that is calling to make an appointment in a restaurant, and when it's mixed with the NLP, then you get to understand what a person speaking, and you get your character to speak. And I think faster than we think, you will be able to just have a casual conversation with the NPCs in the game. And one of the main ingredients for this is speech synthesis. So that's all the motivation why we are investigating these technologies. How it works at very high level. Text-to-speech. I'm going to focus mostly on text-to-speech, not talk much about voice conversion. In fact, not at all. We have a text. In that case, 2021 will be better, Mr. Burns, and we want to produce a WAV file. Fair. So the first thing we have to do is play around a bit with the text. Because 2021, you don't want your system to say 2021. You want it to say a real word. So you have to change everything, every number into their transcription, and you have to expand the abbreviation like Mr. there. And once it's done, to make it easier, you have for the machine, you have to translate everything into phonemes. This is not always needed in every model, but most of the time you will get better results if you train with phonemes, or even better if you train with a mix of both letters and phonemes, if your model supports it. So basically phonemes are like not acoustic units, but because it's another thing, but it's symbols that represent the sound that you would make with your mouth. And as you know, there's different letter. The same letter can have different sound depending on the surrounding letters, and some sounds are made with the combination of 2 letters. So you have to make this translation to make the job easier for the model. And then you have an acoustic model. The acoustic model is in charge of reading these phonemes and transforming them into a series of parameters. Usually they are equally timestamped, and those parameters can be, but not everything, but usually before you had pitch, voice on voice marker, or sometimes LPC coefficient, and at some point MFCCs. And now with deep learning, you will often see a MEL spectrogram, just like frames of FFTs that have been changed into a different scale for frequencies. And then from this series of parameters, the vocoder's jobs will be to translate this into a series of samples. This is the last part that is making the really the wave file that you're gonna hear. Maybe some of you are wondering why we just don't invert the spectrogram if we can predict it, but it's not possible. Usually you don't predict the phase for the spectrogram, and in that case there's not a one-to-one mapping. You cannot reconstruct if you don't have the phase information. This is one reason, and the other reason is usually it's simpler and more meaningful to predict a mel spectrogram, and in that case you have since the frequency scale is compressed, you cannot really invert it and create something that sounds realistic. The last two models, since at least 4 years, they have been increasingly replaced with neural networks, big neural networks, in fact, gigantic neural networks. And each time something crazy come up of in the machine learning community, then there's a new model that is proposed, both for vocoder, and the acoustic models. At the end, I will show you, give you like a tour of the basic component in the model, so you get to size a bit the type of model that we are using. All right. So the main part, controlling the style. How do we do it? Just before I'm going to share with you a little internal demo. This is not something that we ship in a game. It's just a test that we made to see how it sounds in a real game setup. So it's just a video from Watch Dogs Legion, a game that we released last year.
Ah, London, what a town. History around every corner and a tourist photographing it. Pubs serving up a pint and a smile. All that music, theatre and art, the multiculturalism, and the world's oldest underground, the Cube. The class of cities really top shelf stuff. Only took 12,000 years to build it up. And one night to tear it all down.
What's our status?
Perimeter security's down, but plenty of your flying friends about. Dalton, no time to waste.
Yes, ma'am. I mean, any idea what we're up against back?
If you hadn't brushed off, I might.
Ever consider leaving the security threats to the authorities?
That's Rich, Bagley. The government would sooner arrest us for trying to help than actually do something useful.
We'll have to solve this one on our own.
Carefully, Dalton.
Bagley, are you detecting a little worry in Sabine's voice?
Brilliant. Asking the computer about feelings. This explains so much.
Shut it, you two, and get to work.
There she is.
So yeah, as you probably have guessed, every voice there was synthetic. There was sometimes that we needed to match the animation, the facial animation. So at some time we had to do some manual correction, or maybe take a sentence that does not sound as natural as it would, just to make it work with the animation. But that's basically the state of our technology. And now I'm gonna tell you how we make sure that we have different style. Because as you probably noticed, this is very different from like personal assistant, like I don't want to name any personal assistant, but you know who they are. And when you ask something to your phone or your little things, it's rarely angry at you, or hopefully you never make it cry. I hope. Otherwise, you are very, very mean. So we have to deal with all these types of state and style speaking that other company don't have to. And what I'm trying to show here is how we deal with this and how we instruct the model to speak in a certain manner. So why I've been cautiously avoiding saying emotions, because we are talking more about speaking style. It's because the way you speak is driven by much more than just emotion. And also emotion is something that is very difficult to define. Classically, you will hear like people talking about the 6 emotion, the 6 Eggman emotions, in which there is anger, happiness, and surprise. But it's never really fitting. First, there's many ways that you can be angry, and or happy. And you don't want to assign just one label to all these types. You want to have a finer control on this. And also, like if you can have an angry surprise and a happy surprise, so it becomes very difficult to have categories. So this is one of the reasons why we don't try to drive exactly with names of emotion, but there are more. Just when you speak, depending on if you are shouting to someone, shouting order, just talking, or whispering, then it's not really an emotion, but it affects a lot the way the model has to predict the files. And also, just the fact that you can, if you are surprised or you have an exclamation, or if you are asking a question, usually your pitch, it's not an emotion, but if you are asking a question, usually you will end the sentence by raising the pitch, like, do you hear what I'm saying? So you're going to do this thing, and this is not an emotion, but you have to control this if you want to have realistic speech. And finally, more subtle, it's the context in which you speak. I guess the easiest example is if you have like hockey game announcer. It's not an emotion, but he's not talking like he would talk in the street. So what the context on what the person is doing also have a very big influence on this. And yeah, and then you have some other example on the slides, like being drunk or narration. This is a fun one. One of the game that we shipped is a discovery tour, where it's like a guided tour into the past in the setting of Assassin's Creed. We wanted to use speech synthesis, and we quickly find out that if you just record people reading books, it's not the same as having someone explaining what's happening in the scene, and just this subtle difference in the tone, it makes it work or not. So just narration, if you are like doing voiceover in a documentary, you won't speak in the same way as if you are reading a book, like as a narrator. So we have to somehow take care of all of this. So I have a, maybe if I did not hammer the nail enough, we can play this little game, which is named that style. So I'm gonna play some example, and you come up with a name, a category for this style.
I am speaking in a style, and you have to name it. I am speaking in a style, and you have to name it. I am speaking in a style, and you have to name it.
So it's pretty difficult. Maybe some of you had some ideas. So let's do a second game. Think of all the names of the yeah, she's from England. Yeah. So think of all the categories that you would like to cover with the system. So now it's not just name this, but think of all the names that you would like to. So this is already very difficult. And then let's do a third game. Agree with your colleagues on what these categories should be and what goes where. So clear, like very quickly, you will realize that you cannot name these things. It's too difficult and it's impractical. So if you want to have some control and be able to use this, you have to find another way. So yes, there is hope, and I will show you how we're doing later. So I'm gonna just go over some architecture choice that you can do for the models. So there's the first one is just a basic architecture, and you train it with what you have, and it generates. So it's pretty cool, simple to use, very plain, and this way it's kind of data inefficient because you have to train with if you want to get something kind of like good pronunciation, you might need at least around 10 hours of recording from one person. So it's not perfect, and as you see, there's no input for style, so you cannot do anything with this. Yeah, this is a little tip that I added, is you should jazz up everything with some post-processing. If you have signal processing expert, you're going to save a lot of time. But so what can we do? First thing, like a very simple idea is like, let's train one simple model per emotion or per style that you want to use. So we've did that, and here are some examples. So in that case, the style is in the data. As I said, we record like just a happy data set from a person, and when we want the sentence happy, we just use this model. So here's an example.
When I trained it happy lines, I generated happy lines.
And then we have a data set where our friend is angry.
If I train only with angry lines, then I am angry all the time.
But as I said before, like angry is a spectrum, and in that case, you don't really choose which types of anger that you're gonna get. So one way to circumvent this is to put some stochasticity in your model, the acoustic model, and then you never get the same line. So you generate several and you choose the best one, the one that fits the best for you. So again, it's a simple idea. It's easy to use. Data inefficient. You have to record a big data set for every types of speech that you want, and you know nuances. I mean, you don't have control on them. As I said, you can generate and hope for the best, but it's not that cool. So yeah, that's option one. Option two, which I don't like, and we never did, is you can train everything and have a style encoder. So you put everything in the same data set. You have all the style, and when you are generating angry, you just put the tag angry, and the style encoder in that case it's probably just like a regular embedding. One hot vector that is pushed into just an embedding layer, and you would get something decent. In that case, it's more data efficient because you are leveraging all the other style. Let's say you have a couple of angry, a couple of happy, a couple of whatever. To learn to speak just pronunciation and the base language, then you can use all of them. So in that sense, you are saving a little bit of data, but it's global control only. As soon as you are putting more different style, less tightly guided style, you're gonna hinder the pronunciation. It's gonna be less clear. And also, because the prediction of the acoustic model are lesser quality, the vocoder will have a more difficult job, and the sound quality will suffer from it. And as I think I've been making this point a lot today, it's difficult to define the styles that you want. So you have to put name on them, and again, you don't really control the nuance on style. So that's good, but it's not perfect. Option 3. This is the one that we've used to make the video before. In that case, what we do is that we use an example that we encode, and we say to it's a way to tell to the model, use the text that I just wrote, but I want you to speak in the general style of this example. So it's gonna transfer the style to the new text. So maybe we can hear some example before I go over the pros and cons.
I don't believe she was in school at all, said Anne.
So this is an example. We have no name for it. It's just that's the way we want it.
Using examples to condition generation gives me more flexibility.
Then I'm gonna give you two more examples that have been applied to a new text.
Tom and our lawyer asked them some questions. They stuck to what they said. If you use an example fast, it talks fast.
I see you have a sailor's eye and have got your wits about you. When the example is slower, speech rate diminishes.
So in that case, I've showed you like the general transferability of a style, but I took special care of taking two types of angry lines that we have in our data set, which sounds very differently. I didn't have to find a name for them. I just listen to them and say, okay, yeah, this would be good in my scene, and then I could use it. So this is one big advantage. You don't need to define style. It makes it very data efficient, even more than in the previous example, because in that case you can leverage everything, and the model doesn't have to really guess what's happening. He has a pretty good idea of how it's going to go because he has an idea of the global style. So it helps a lot getting a better pronunciation and attention and everything. In that case, it's better to use only one model per person, and you only have one model for everyone. So that's cool compared to the option of having different model per emotions, and you get a bit of control on the nuance. I put simple to use, but to be fair, it can be daunting to go over thousands of lines and listen to them to find the style that suits you. And there are other way to go than just clicking and listening. You can visualize embedding and stuff like this, but I don't really have time to go over this, but there are solutions to make navigation easier. The cons is you only have control on the global style. You cannot go and change things very finely, and it will pronounce in lousier pronunciation and lower sound quality than having just a big model, single model with one style, with a very big data set. But you have to make compromise if you want flexibility. And there are other options, but I won't go over them because I don't have time. I don't want to take too much of your time. But there is new model where you can go and change locally parameters with you predict some parameter like pitch duration for all the phonemes, and then you can manipulate them by hand. We're working on this. Soon we will publish a paper where you can get all the details on that. So I just want to give maybe a bit more detail on what's in all these boxes. I still gonna stay high level. I think it's late and not everyone wants to see diagrams of layers and stuff. So what's in the front end? The front end is just a lookup dictionary at this basic form where you go and look at words and you get their phonetic translation. But it's more than that, because there's different words which are homotypes, but they are not homophones. What I mean by that is that they are written the same, but they don't sound the same depending on what is their function in the sentence. I guess that the use is he thought it was time to present the present. Present and present, they are written the same, but in one case we say pre, and in the other we say pre. So it's different phonemes. And to understand which one is which, You cannot just do a lookup. You have to make some grammatical analysis and realize, oh, this time it's a verb and this time it's a noun. And then you can get the good translation. And also there's something a bit more intelligent, because sometimes there are words that are made up that are not in the dictionary. So you have to support this as well. So this is all done there, but it's mainly scripts. Once you get the phonemes, it goes into the text front end. The text front end is basically a couple of CNNs, and on top of this, there's our RNN, and it's going to create a matrix of the representation of the sentence. So you will have, in this matrix, it's going to be like a big memory, and for each time step will be a phoneme, and there will be like an internal machine code that can be read. I don't know, like, if you thought about this, but if I say a sentence and you say a sentence, it probably won't have the same length, and maybe some letters I will say them faster than you, and maybe some other slower. So that means that you have to have some way to pace yourself while you are generating, because you cannot predict how long it's going to take to say the sentence. So that's why in this solution, there's an attention module. And the job of the attention module is to look what he's been saying and what he has to say, and tell, okay, now I'm reading this. And like if the phoneme is a T, it's something that is very fast to say. It's a very short sound, while A, for instance, takes a lot more time. So in that case, the attention model will slow down its reading. So it's mainly like a monotonic reader with a different speed depending on which phonemes he's trying to say. So this is all learned end to end. And the attention module, it will send a representation on what he's reading in the matrix, and it's going to be decoded by a couple of RNNs and some fully connected layer at the end, just to format a bit the stuff. This is loosely based on the tachotron model, but is like an industry standard. I don't know if I should say industry standard, but it's a standard model, a standard acoustic model. And then what you get is a mail spectrogram in our case. So this is our representation, and from this representation, at that point, we know exactly how long the wave file will be. All we have to do is to expand the mail spectrogram into like a couple of samples, and then we condition some RNNs, and the RNNs will predict the samples one by one. In that case, it's loosely based on wave RNN. Maybe the most well-known model you might know is WaveNet, which is a recursive vocoder. But yeah, we found that this architecture is more robust to different types of sound. So maybe you've noticed I did not talk about the styles. So this is what we're going to do now. First thing we do is we change the example into a spectrogram, same representation as the one we are trying to predict. So you can see what I'm saying from now on. Like this model, you flip the way you see it. It's not text-to-speech anymore. In fact, it's an autoencoder. It's a speech autoencoder. So we go from spectrogram to spectrogram. And in the middle, the reconstruction of the decoder is conditioned on the text. So the style encoder, it's a bunch of RNNs with CNNs. Also, I did not write it, but there's a couple of layers, fancy stuff, that will transform the whole sentence into a single vector. And what we use as representation space is a VAE space. So that means that every point in that space is, in fact, representing a little Gaussian that is constrained to be near the normal Gaussian, the regular Gaussian, centered at 0 with one variance. This is a regularizing term that makes every point a distribution, and then you sample into this, and this is what you use to condition the model. So I hope it was technical enough and not too much, but yeah, that's how it works. All right. So quick conclusion. Just gonna show you one little trick that we use. This is a secret. Don't tell anyone. So one way that we get model that speaks well, that learn a good pronunciation without having to record every actor for 10 hours, is that we train one model with everyone. And we use a speaker encoder, and that instruct the model, say, oh yeah, you can read as you would always read with anyone, but when you speak, I want you to use this voice, the voice of one person. And then you can go in the internet and download very big data set with hundreds of speaker. And if you train this way, then every speaker, they will benefit from the text that has been recorded by the others. So this way you have a huge data set and you learn to speak like everyone. So that's nice. Once you did that, you have a pretty good text encoder. So all you have to do is then do some transfer learning, and you focus only on the new voice that you're trying to acquire. And you can conserve at that point. In our case, we train without a style encoder at first, and once we're done, we freeze the layer, and we add the style encoder, and then we focus only on the one or two speaker that we want to be able to control. But there's a problem, and this is the model that you've heard. In fact, I was lying before. We pre-trained on many people. It's just that at some point we forget about everyone, and we put only one speaker. And we finish the training with the only person. So in that case, I would have an example of angry line and put say talk with this lady, and I would hope to get angry line with this lady. But is it what we're really gonna get? Most of the time, what you will get is either, in that case, I wanted to speak like the guy, and the example I have is from the lady. I have a lady angry style example, and I want it to be man angry. But in one case, what you will get is it's gonna recopy exactly the style, and in the style, the model will encode also the voice of the person. So there's going to be a leakage into between the two representation space, the one from the speaker and the one from the style. And in that case, if the style encoder has too much capacity, it's going to also encode the voice print, and it's going to discard the identity, and you will get the right text, the right tone, but the wrong person. And what might also happen is that it's just going to disregard, if you constrain too much the style encoder, the style is going to be disregarded, and then you're going to get whatever style the model decide to speak with the right identity. So this is like a very big research question: is how do you separate these two encoders, and how do you make sure that everyone is doing his job and only his job? And this is what we are working on. We have something quite interesting that we're going to present soon, that we're going to publish soon. So I guess I'm not going to spoil it, and just to tell you, stay tuned, watch closely. It's gonna happen soon. We believe that we got the state of the art in style transfer, inter-person style transfer. So,
do you think out of distribution generalization can help in having NPCs that behave and talk randomly, like real conversations, like we have in the real world? For example, when walking at the park, you have people around having a real conversations.
Yes, I think that the problem is not really on the speech synthesis side, but more on the NLP side. It's you have to generate the content of the conversation to make them look interesting, and also having text is just not enough, as I have showed in the presentation. If you want it to sound real, you have to add some style, some intention. So you would have to also predict some kind of intention space or some kind of style space with your text, which is totally feasible. In fact, there's some papers that are addressing this. But I guess one of the big challenge that we have for video games, or I guess this situation applies mostly to video games, is that we cannot publish stuff with copyrighted content. And if you ask GPT-3, for instance, to generate text, then it has been trained with a lot of books and stuff, and it's very difficult to guarantee that this will never spit out some passage from like a well-known book, and then you're gonna be infringing copyright. For instance, if you ask GPT-3 what are the laws of robotics, it's gonna cite Asimov. So yeah, this remains a problem that at least an hurdle that we have to address before we have free runnings characters in the games.
Yeah, really interesting point there about just kind of gibbering away some copyrighted content. If the quality of the outputs continues to increase, what would be needed to avoid the use of this tech for non-ethical applications?
I wish I had an answer because I mean I don't know how you can, like, I guess it's the same question for deepfake. How do you make sure that that nobody use deepfake to do wrong things? I wish I had an answer, but the only thing I know is that it's possible to detect speech, like a synthesized speech that has a distinct signature, and it can be, some model can be trained as for detecting deepfake. But then, I mean, what people do with technology is it's very difficult to control. At least I don't have an answer. I admit that it's a big problem, but I don't have the solution.